is happening from the
it's going
experiment 1 to experiment 2.
up by 4.
Going up by 4.
So the rate's getting faster, and chemical C is actually diminishing. So if anything, if C is 0 order, it won't affect it. But if it's first order, it'll pull the rate down in half, and then D has to overcompensate to get it up to second order, or quadruple it. It has to be the third power. Is what I mean. Rate equals if it turns out, if we see the rate double, but if the rate goes up by 4, when you've doubled, if this is the first power for C, and if it's first power, and you just cut it in half, the rate now is going to get cut in half. So that means D has to do all this work to get the rate back up to speed. It'll have to be to the third power. That'd be really hard. So it seems like since you're doubling D, and the rate's going up by 4, maybe that's second order, which means C is 0 order. So one way that would work is if that combo, may not be, but that would work. The other one would be C is first power, D is third power. We didn't really talk about third order kinetics. So this is a more reasonable one. Have something be 0, the other be second order. Play with numbers, I suppose, and see which one will give you a constant for trial 1 and trial 2. The K comes out the same. Find K. Now that you know the powers, you can slug in any of those experiment data, like this stuff. Take that one, plop it in, and you end up getting K is about 0.42 or 0.4. Something in that vicinity, I think. Is that right?
Yeah, 4.1.
0.1. Depends on which set of data you take. It's 4.2 for the first one and 0.413 or something for the next one. After 15 seconds, well, here's simplification. Since C is not involved, second order with respect to D, you probably justify using second order kinetics. Just 1 over the concentration, final. Integrated rate forms. Okay, so using this, we know our K already. Concentration to start was part experiment 1. That's 0.1. So we can find out, solve for this one in 15 seconds, so we know that. What did you come up with for the concentration of D in the end?
0.0616.
Now we have to go back and do a little bit of finagling to figure out how much chemical C there is. C wasn't involved in the rate, but it's still getting used up. It's getting used up in a ratio of 1 to 2. So how much D got used up? It went down by 0.0384. That's how much we lost in going from started at that and then went down to 0.061. So it lost 0.0384, subtract it. But C went down by twice that. Every time one D gets used up, 2 C's get used up. So 0.0768 is how much C is what used up. And it started at 0.4. 3.232.
0.3232.
Is that right?